Okay, so yeah, so today it's our pleasure to have Laurent Orseau. We'll be talking about from time sharing to
Hi, thank you, Amzi. Thank you, everyone, for being here. I'm going to present some work that's been going on for, well, almost a decade now. So mostly done with Levi Lelis, the University of Alberta, but also more recently with Marcus Hutter right here, who came, even though he knows all about this stuff. I think he thinks. And right, so I'm going to talk about time sharing and efficient research and how it comes from AIT more specifically. So let me give you some context. I pressed on something else. So at the origins of this project, there was this the AlphaGo success in 2016 and a bit before that. And the idea is really something quite simple that works extremely well. You first have a domain where you have a perfect evaluator, something that tells you the ground truth. Is it working or is it not working? And you have some parameterized model that tells you maybe how to search in the space that you're looking. And you have this search algorithm on top of it, so MCTS-like here, that allows you to go much beyond what the policy and value function can give you for just one step. And then you have this self-play loop. And when you combine all this, plus the refinement of the policy as you do the self-play, you get something that's very close to recursive self-improvement within a limited domain. But from scratch, you get to something that is superhuman level. And then applied it to some other problems like chess and shogi and so on. And I was looking at all this from the close sidelines, and I was very impressed, and it felt like we're really on track onto something big here. But there are a few things I didn't really like in the details of the project. And at the same time, I was really thinking about Levin search, universal search. Actually, more than thinking, I was implementing and trying different things to make it more efficient. And yeah, it was interesting, but it was also limited. So I felt, okay, on the one side, we have something extremely practical that really works. On the other side, we have something extremely fundamental that doesn't quite work. How can we merge the two? So I'm going to explain universal search in more details just after that. But basically, the idea is that if you have an inversion problem, something where you can verify that you have the solution relatively fast, then you can run a Levin search and you know that you're going to solve the inversion problem just as fast within some constant factor, who cares about constant factors, of the fast and shortest program. So not just the fastest, not just the shortest, but the fast and shortest. But yeah, the constant factor is actually very large in most interesting situations. So how do we deal with that? All right, so that's the inception of it. Okay, so before I talk about how to use or to adapt universal search to our problem, I need to explain the setup that we're considering. So we consider a relatively simple setup. We have a deterministic search problem like this little game of Sokoban, where the green alien needs to push the brown boxes onto the red spots. And we have a tree of possibilities, like you have some actions, left, down, up, right, and that gives you some new states. And then you can apply this. You have a whole tree of all possibilities. And maybe there's a solution here because there's a fast verifier that tells you this is a solution. So this is one of the solution nodes. Okay, so roughly that's what it is. A bit more formally, we consider that we have a deterministic environment. We have like state, action, transitions. We have a predicate that tells us whether something is a solution. We can relax most of these assumptions, but that's not necessary to understand really the gist of it. And we are given a set of problems, and we want to solve all these problems as fast as possible. But initially, we have little prior domain knowledge about these problems. So we need to do some self-bootstrapping, it's called bootstrapping, based on information we can get from what we can observe. So this bootstrap loop works like this. So we have this data set of problems, but we are not given the solutions. And we just hope that there's some diversity in the difficulty of the problems, not necessarily a crafted curriculum. So we don't need to say, here's the simple problems, here's some slightly less simple problems, and so on. We just have like this shuffled data set. And then the search is going to like take random problems or search through the whole set with some fixed budget. And hopefully some of the problems can be solved by blind search. So they are easy enough that we can gather some information. And we update the parameters to better fit the solutions we have found for these problems. We can also use failed searches, actually, in some circumstances. And once we have refined our parameters a little for the search, we search again, and maybe we solve a few more slightly less easy problems, and we refine again, and then we bootstrap this way up to hopefully all the problems that are in the set. If at some point we're stuck, maybe we can just double the budget, try harder, and solve maybe a few more problems. So this is very similar to the safe play loop, except that it's just one player. We don't have like two players that play against each other. And we don't necessarily assume a problem generator to have infinitely many problems, but that can be adapted to that too. So there are lots of applications, even in the deterministic setting for this. So like everything that has this format goes from theorem proving to some program synthesis, protein folding, drug design, material design. Lots of problems this way. Even if you have a random environment, actually, you can just fix the seed and do some search, like this deterministic tree search, and then you just vary the seed multiple times. In our work, we have focused mostly on puzzles because they are very useful benchmarks. The first reason is that, well, they are easy to implement, easy to run, fast to run. The objective is clear, it's intuitive. The difficulty is easy to tweak. The domain is even easy to tweak, like you can make it slightly more difficult and so on. And yeah, so, and also it's a bit fun, so that's good to go with. Right, now we are very interested in searching, consider search algorithms that have some kind of guarantees, but what kind of guarantees? So one very classical guarantee is on the solution quality. So whether the solution is very short or close to the shortest solutions. This is the realm of algorithms like, well, breadth-first search, sure, and also A-star. And if we relax a little, weighted A-star, because sometimes finding the shortest solution is close to intractable. So if we say we find some short-ish solution, maybe that's good enough, and we can speed up the search. But even that sometimes is also quite intractable. But well, the good thing is that we can use weighted A-star kind of algorithms with neural networks and combine them to do this efficient search with a parameterized model. So that's what they do. They did, for example, with DeepCube A. They had a Nature paper that was quite nice. Even though with a neural network, you don't have this required property for A-star, which is admissibility. Well, when you use weighted A-star, you might say, yeah, maybe it's 1 plus epsilon admissible. It's fine. Another guarantee that you can look at is regret minimization. So the idea here is that when you do the tree search, you get some rewards, and you want to spend most of your time under the branch of maximum return because you want to get the most rewards overall as you do the whole search. But actually, this is very problematic for tree search because tree search is basically an exploration problem. And if you minimize regret, you're going to spend most of your time not exploring. And so it's going to take you a lot of time finding solutions that are elsewhere. I have a more detailed explanation about this in the slides at the very end, but only if I have time or if you come to me afterwards. So this is the realm of algorithms like UCT and MCTS algorithms like have been used in AlphaGo. And I'm saying this doesn't work, but yet it did really work well in AlphaGo. But they used a lot of compute. And once you have a good policy and a good value function, it's fine because you can be mostly greedy and it's going to work well. But the exploration going to this good value function and policy is suboptimal. Okay, blah, blah. And the last guarantee, the one that we are really interested in here, is searching fast. So if we take, for example, breadth first search again, we do have a guarantee on the time it would take to find a solution. If the solution is at depth D and we have a branching factor B, it's going to take at most B to the D steps. It's exponential, it's not great, but it's the worst case, and it's a baseline that you need to consider because, well, sometimes that's the whole thing, that's only what you can do. We consider a setup where we have these parameters models, and then we want to give guarantees that are more sequence dependent, instance dependent, and quality depending also on the quality of your parameters. So this is the LTS and root LTS algorithms that I'm going to explain. Okay, let's go back to time sharing between programs, which is the root of Levin search. So what is this? Imagine that you have a problem that you want to solve, and you have K programs that can all solve the problem in some time. Maybe some won't solve the problem. And when one of the programs find the solution, it just holds. You have some weights on these programs, WK, and the sum of the weights is 1. It can be less than 1, but not more. And you just have one CPU, and you want to run these programs in some way to solve the problem and have some guarantee. So the idea is that you are going to share the time between all the programs in some way. So by dovetailing, we mean that we run one program, then we run another program for some time, then maybe we run the first program for some time, some more time, and then back to the second one, and then the third one, and so on. And we ensure that we are going to spend WK times T step for a global budget of T steps for program K. So the sum of the WKT is at most T. So we are sharing the time without overbooking, basically. And now the meta algorithm is going to stop as soon as one of these programs finds a solution. And the question is, when is it going to stop? Well, that's actually quite trivial when you look at this. If you have one of the programs that stops in TK steps, and you know that you allocate WK times T steps to that program, then you just invert the formula, and you find that T is going to be at most TK over WK. So TK running time of the program K, WK, the prior of program K. And because this is true for all the programs that you have in your batch, you actually have a bound that's guaranteed to be over the minimum of the programs of TK over WK. Okay, so that is the time sharing guarantee, and it's very much what Levin used in the universal search algorithm. So now we just consider that instead of a fixed finite set K, we have all possible programs in some given programming language. We just assume that the programs are written in a prefix encoded way, which is relatively easy to ensure. And we give a weight of 2 to the minus the length in bits of the program. So that's the Solonov prior, basically. And this, by crafting inequality, tells us that the sum of the weights is going to be bounded by 1. Great, so now we have our prior. And we use, instead of a dovetailing schedule, we use a restarting schedule where we start at T equals 4 steps. And then we look at all the programs that run for at least 1 step. So we look at WK times T, take the floor of this. And if it's more than 0, if it's at least 1, then you run the program for that many steps. And if it finds a solution, you stop it. And if it doesn't work, you double the time bound T, and so on and so forth. And that's it. That is Levin search. That's the universal search algorithm. And the cool thing is that the restarting schedule only incurs a factor 4 on the bound that I showed earlier. That means that you're only paying a factor 4 compared to the minimum of all the programs that may solve the problem of the time divided by WK. I'm removing the plus ones because it's not that important. Now, WK is 2 to the minus length of the program in bits. So 1 over WK is 2 to the length in bit of the program, which is pretty large, obviously. It's still kind of the best you can do if you have no more information or no more data sets, say, or to train on. But obviously that's also not tractable and we can't really use that directly. Like I tried, it doesn't work. You can only do so much with it, like simple, small programs, but that's it. Not something really interesting. Okay, so knowing this time sharing algorithm and looking at how practical this AlphaZero thing is, how do we merge the two? Well, I figured, okay, the problem is, in part, is the programs. We probably don't want just the program as it is, as they are, because, well, the right program is going to have a very small prior. We want something that we can tune, like we can learn. So maybe we want a parameterized prior, but just having a prior over all programs and having one weight per program is not going to help much either. So maybe we want something like a composable prior, that programs are made of bits that you can compose, and then you have a prior over these well, functions, maybe if you want, that you can compose to generate all your programs. And then you can learn some prior that is more adaptive to a set of problems. Okay, that's nice, but maybe there's something more. Maybe instead of working at the program level, we can work at the instruction level. When you think of it, you don't really care about the programs per se. You care about executing the programs. You care about the trace of the program, so the sequence of instructions that you use to find a solution. So now if you look at a particular sequence of instructions, a 1 to t, for example, t steps, well, there are many programs that can generate this sequence. So why just look at just one of the programs? Maybe look at all of them together if you can. And if you look at the sequence of instructions and you take a prior over sequences of instructions, well, you get a prior implicitly over all the programs that generate this sequence. Okay, so that's interesting. And it turns out that this is very much the policy prior in AlphaGo, right? Instead of instructions, you have actions. And then you have a prior over sequences of actions. And when you do the search, you have this whole tree of action transitions. Okay, so that's a good start. How do we do that? How does it look like in when we look at the bound for time sharing? So now we have a sequence of instructions corresponds basically to a program, or rather a set of programs. The runtime is going to be the length of the sequence, so the depth of in the search tree. And the prior is going to be the probability of this sequence of instruction, which is basically going to be the policy prior of the whole path from the root to the node that you're considering in the tree at depth d. And that gives you that the time it takes to get to this sequence of instructions is bounded by the depth divided by the policy prior of the sequence, which is the product of these properties. Okay, that's great. That's a good start. So that's the interesting thing here is that here we're really merging all the programs together, and instead of having just one element in this set, we're taking all the elements at the same time. That's great. And that's exactly, or almost exactly, the Levin tree search algorithm that we devised in 2018. The idea is that you have this policy object, the standard policy object over the actions in a given state. You just assume that it sums to 1 at every state. And then maybe you have a node n star here as we did it before. And Levin tree search is just completely defined by best first search with a cost function of depth of a node divided by path probability of a node. That's it. That is really just that simple. So if we calculate what it is here, in this node here, the depth is 0, 1, 2, 3. The path probability is 0.6 times 0.4 times 0.9, which gives a number 13.8. And so that's the cost of this node. And now this other node here is at depth 2, has a path probability of 0.1 times 0.1, which gives a cost of 200. So what this means by best first search is that you're going to visit n star before you visit the other node. That's it. Okay. So this is just really what I said. You can also have some pruning, like you remove branches that are you know that you can prove that are not they are not going to be useful. This is the path priority definition, and then the guarantee we have is what I said earlier, like the time sharing guarantee, which is this D over pi, so time over prior of a sequence of instructions, sequence of actions. And what's really interesting here is that when you look at this big infinite search tree and you look at this node n star, you know that the time it takes to get to n star is bounded by 15 here. So that means completely independently of what happens in the rest of the tree, like this big part, you can have extremely long chains, you can have huge branching factors. It doesn't matter. You know that after 15 steps, you have visited n star. So that's a very simple guarantee that we just took from like 50, almost 60 years ago, to turn it into a practical algorithm with a simple but yet quite effective guarantee. Okay, so with that, we started some experiments in 2018. We didn't use the bootstrap loop at the time. We used something else, and we tested on Sokoban. So the design has changed a little over time. The data set that we're using ranges from like trivial problems to mild difficulty. For a Sokoban expert, they are going to be relatively easy, but some can give you like a little pause, though. It might take you half an hour to solve. There's a huge variance among players. Right, so we trained on this, and at the time we were using A3C to train the policy, and we even were giving intermediate rewards, like shaping rewards, to help the search during training. And at the time, we managed to solve 65% of the training set with this. In hindsight, that's actually a relatively poor number. It's almost amazing that we got something out of that. 65% of the problems are relatively simple. But still, when we used Levin tree search at test time, we managed to solve all the test problems in a decent number of expansions. Wasn't that great, but it was a good start. Now, the next paper, we actually used Levin tree search in the bootstrap loop to really try harder to solve all the training problems and get something better, like a more autonomous pipeline. We removed the intermediate rewards. And then we got something that worked quite well. So twice as fast as what we had before. So on the right track, and also more autonomous. Great. We are using neural networks for the parameterized policy also. What's interesting in this last paper is that we went from a guarantee to an objective function. So when you have a guarantee, if this guarantee is tight, then maybe that's what you want to optimize for. You want to optimize here the search time. So if you have a guarantee like lower bound and upper bound on the search time, then you want to push it down. Like you have a set of problems, you have found solutions for these problems, you have some parameters, and you're going to say, well, I want to minimize the upper bound on the search time for all these problems that I could find, could solve with respect to my parameters. And of course, you need some regularization because you don't want to be completely overfitting. Otherwise, you're not going to generalize to later problems. And we use that, and indeed, that works very well. That tells you that you look at the numbers during optimization, and you know for sure that if you solve the problems on A, again, it's not going to take you more that much time that's written on the screen. I have some slide, but I'm going to skip this one about how this loss function is more adequate than the log loss cross entropy that we're usually using for the policies. For optimization, at least for that kind of algorithm, like Levin tree search or even sampling. But I can give more details later. There's an exponential gap, basically, if you're not careful. All right, the next part, what time is it? The next part is about my discontent with neural networks. So for quite a while, I've been bothered by neural networks. They work well, yes, sure, but should they or do they do what we want them to do? We are not too sure. Like we lack strong guarantees about what they're doing, and if we can use them to the most efficient in the most efficient way. So we wrote a paper where we substituted neural networks with a different kind of model, parameterized model, that came from this idea of being able to compose programs. So you have these programs that are made of multiple blocks that you can compose in many different ways to write many different programs. And you have a prior over these blocks. That's great. But how do you do that so that you have high capacity and you have a guarantee that you're learning the right thing? So guarantee that you're learning the right thing is basically something like convexity of your loss function with respect to all your parameters. If you have convexity, then you know that you can use some kind of gradient descent to get to the bottom of your loss function and ensure that you have the best parameters for your set. For neural networks, they work well. We have lots of tricks to make them work even better, but we still don't have any convergence guarantee to some class. We don't know. Maybe if there's one layer or like infinitely wide, then yes, but that's not what we're using. So we're using context models, which is not really new in this paper, but the way we use them maybe is a little new. It comes from the compression literature from years and years ago. Again, an old idea. And the idea is that you have many experts. There are small experts that do just a little bit of work, each of them, but you're going to use them together to have a strong predictor. But not only that, but you actually have many, many, many experts, but you only use a subset of these experts at every step. So maybe you have many parameters. So it's like a big mixture of experts, but sparse also a mixture of experts. So that's very efficient on a single CPU because you only have to know which parameters you're going to use, have a small softmax basically. So it's like a more logistic model or log linear model if you want, or it's also product of expert or geometric mixing. There are so many names about it that it must be fundamental, right? Yeah, maybe we need to say that it's also gated or contextual. And the good thing is that these models are convex for the log loss and for the LTS loss function that we saw just earlier. So that's great. So we have these guarantees to converge to the optimum. We also need some regularization. And intuitively, these models are good because they allow you to have both generalization and specialization at the same time. For years, I was stuck at either, and I couldn't get both at the same time until I look at the guy next to me, sitting next to me for years. He was doing just that for years, and I just forgot to listen. And why they work well is because they can make use of this wisdom of the crowd. Like every expert has a little bit of information that allows you to be a little better. So you don't just want to use the average of the predictions. That doesn't work well. You want something nicer, smarter. And they can be very surprisingly effective. Like they surprised me a few times. I was removing stuff to make them simpler and it was still working. I was wondering why it works. And eventually understood, but yes, you don't need that much complicated models to make them work very well. And as I said, they are very fast even on a single CPU. So you don't even need a GPU most of the time, at least not for the experiments we're doing. Okay, so why do they work well? Imagine that you have this little grid world here where the triangle needs to go to the green disk. And we know that this red triangle comes from the left. And we have a very simple context model where we have just 5 contexts. One of the contexts is look at the cell to the left. Another one is look at the cell up, and then right, down, and also look at your last action. That's it. That's the context model. And then every context, you associate a distribution over your actions, the probability distribution over your actions. So the left context says, well, there's a blank cell on the left. I don't know what you should do. You can go left, sure, but maybe you can go up, right, down, I don't know. I'm completely agnostic, so uniform distribution. the context on the top says, yeah, same thing. I don't know, like it's a blank cell. You can go there, but you can also go elsewhere. A uniform distribution. So these don't have much information. Then the context on the right says, well, there's a wall on the right. I don't know about the other actions, but going right has never worked. You can't solve the problem if you just go to the right. That doesn't work. So just do something else, up, down, or left, but just not right. And the other context that looks at the bottom says that, yeah, there's a wall on the bottom, the down action. So just don't go there, do something else. And the last context says you come from the left. There's no point going left. Just do something else. Don't do left. So what you see here is that if you have a large branching factor, every expert is going to tell you not this action, not that action, not this one. And then you shrink your branching factor quite a lot and make your policy much more effective. So here we just take the product of all these, we renormalize over the actions, and that gives us this product mixing value here, which is a distribution with a peak on the action go up. That makes a lot of sense. And what's nice is that every little context only looks at just a little bit of information. So on Sokoban, for example, what we did is we have like this tiling operator. It's nice for a 2D grid world. 3 by 3, a bit around the agent, and then 4 by 2, 2 by 4, and so on. And that gives us a bunch of context to look at every step. To each of these contexts, we associate these parameters. We calculate the product mixing that gives us the global policy over the actions. And as I said, these are all composable because every context can appear at this state, but maybe later in the search also. And they define basically a composable prior on the instructions that themselves define a composable prior over the programs. Okay, so with it, we had some very nice results. On Sokoban, we reduced the search time by the training time by quite a lot, from days to just 1 hour without GPU. On the test set, we got some good numbers also. Like it's not mind-blowing, but it's pretty nice. And the test time is also much better. So to be fair, though, the previous paper wasn't using the best code base ever, but still it shows that it can be quite fast. And then we tried on different problems. It works well also. There even was one problem where we couldn't make Levin tree search with neural network work on the sliding tile puzzle 5 by 5. And with context models, it worked out of the box. Blah, blah, blah. Okay, and we also tried it on Rubik's Cube, and it works also, like bootstrapping. You just give a large number of problems with varied difficulties, so you scramble a little or you scramble a lot. And the context model is actually quite simple. So when I designed this context model for Rubik's Cube, I figured, yeah, this tiling operator, it's not a great fit for this 3D puzzle. It's more relational, so maybe I'm not just going to use that. But I still want something so simple, something where I don't give a lot of domain knowledge. I don't want to say, oh, there are all these symmetries, all these long macro actions. So no. I just want something quite simple, generic, reusable. And I figured, okay, so these Rubik's cubes, they're made of little cubies that the moving pieces. And maybe one context can be one of these pieces. Then I calculated the number of configurations, the number of possible parameters that this would give me, and clearly that wasn't enough. Like the Rubik's Cube is a complex problem. I'm not going to solve the Rubik's Cube with just 100 parameters. So I figured, well, if one is not enough, let's just take two. And if we take two cubies, the number of configurations suddenly, well, is quadratic. And that gave me a significant number. I thought about 3 also, but 3 seemed like a too big number, so I just stuck with 2. And what this gives you is like you to look at every pair of these cubies. You look at the configuration in these pairs. That's each configuration is one context. And you take the product mixing. So each expert really is only very locally informed. You take the product mixing of their prediction, and that gives you a policy that eventually can solve every Rubik's Cube within 500 search steps. So even with something so simple, you can devise a very efficient policy on such a complex problem as the Rubik's Cube. But not only that, but that was in the bootstrap loop. So it got from it doesn't work at all. We are completely blind the search to something that eventually learns to solve more and more cubes up to solving all of them. Well, there's an unfair, well, not unfair comparison, but it's a different objective, so we can't really compare the numbers directly. Let's move on to the most interesting part of the talk, at least from my perspective. So the root LTS algorithm is a new algorithm from a couple of years ago that reuses the time sharing that we saw at the beginning in a quite different way from what we did before. But it's still based on LTS, just that we route it at different places. So how does it work? To explain why it works and how it works, let me introduce a motivating example. Imagine that you have a node n star here in a binary tree, maybe infinite binary tree, but this node n star is at depth 100. So if the policy is uniform, then the search time is going to be 2 to the 100 for breadth first search. That's intractable, basically. Now, the thing is, we have some mild side information at some nodes at depth 50. So some of these nodes, actually 1,000 such nodes at depth 50, are telling you, maybe the solution node is behind me, below me. So maybe if you search more below me, you will find it. Okay, so that's great. That can really be helpful, but you also need to consider that there are also 999 misleading clues. So you need to be careful about how you manage your time, how you share your time. And MCTS is actually very bad at this time sharing business and can be misled completely by any of these clues. Eleven tree search in itself is not going to help much here, because when you have such a clue, you look at a node, okay, there's a clue, maybe you just follow the clue once, but then what do? You have no more search information, so you still have probability 1/2 to go left or right, and before you see the clue, it's also going to be probability 1/2. What do? It's not going to help much than this one step in the middle where you see the clue. But there's a very simple strategy here that's going to be more efficient and optimally efficient, even though it still takes a lot of time. The idea is that you're going to search initially at the root down to depth 50, and you find all the clue nodes, the 1,000 clue nodes, and then you stop the search. And then you start the search again under each of these clue nodes from depth 50 to depth 100. And one of these is going to find the node n star. So the number of search steps is going to be 1,001 for the root times 2 to the 51, basically, which is a lot less than 2 to the 100. Still a big number, but it's almost the square root of 2 to the 100 times some factor, which is the uncertainty of where the good clue is. Okay, so the idea now is to do time sharing between all these clues. Now we assume that we have some side information that we get from somewhere. We have something called a rerouter that is going to allow us to try to search at different places with different time sharing. So you take the Levin tree search algorithm and you start it somewhere at the top of the search, on the tree of the root tree. Of the root of the tree, and you search for some time, and then at every node in the search tree, you're going to start also LTS with some time sharing weight. So you ensure just that you have some good time sharing weight at the root, and then you're spreading the rest among all the other nodes. So there's a lot of overlap between all these searches, but if you're careful, that can be very efficient. So now the idea is that if there's, for example, a clue node somewhere that tells you, maybe the solution is there, then you assign a higher time sharing weight and you spend more time under that node. So we call this, basically you have a probability distribution, like the time sharing weight. So we call that a rerouting weight, W. And the question is, what kind of guarantee can we hope for now? Like we have this time sharing guarantee earlier from the programs. What can we hope for? So we have the programs or the LTS searches. We have the weights W for each of these programs started at the node N. This operator here means precedes, so it's higher in the tree, ancestor of. And that is descendant of, basically. So we start these LTS instances from every node, and one of these is going to find the node N star the fastest based on the time sharing weight that we have given. And we know that at this point, root LTS, so the meta algorithm, is going to stop and say, I have the solution. And this time, what bound can we expect? Well, if we just look at the previous time sharing bound, it's going to be the minimum over all the instances that we have started of the time that we take alone divided by the time sharing weight. But there's something not quite right here. And let me explain what it is. So if you look at this search tree here, so imagine that you go from N1, and then there are some nodes in between, and then that's a node called N2. You start LTS again with some other time sharing weight, and then there are some nodes, and then you get to N3, and you start again LTS with some time sharing weight, and eventually you get to N star. And if we look at this bound, it says that, well, the time is going to be bounded by the time it goes from N3 to N star divided by the time sharing weight. But that can't be right. Like, maybe this is super hard to get to N2 or even to get to N3. So that can't be the only thing that we need to look at. And the reason that we can't directly transpose the time sharing over programs into the setup is because we have this tree search constraint. Nodes need to be searched into some order from parent to child. So maybe what can we expect now? Maybe you can look at maybe the sum of these segments, like, okay, the fastest way to get to N2, and then the fastest way to get from N2 to N3, and then 3 to N star. Yes, so that works, but this is actually wasteful. It turns out what we can do a lot better. I was using this formula for a few months until I decided to write the proofs more formally and realized, wait, actually, I can just use a max. I don't need a sum. I can just say, well, the most difficult subtask, we call that subtask, going from one node to some descendant somewhere on the path to the solution. So the most difficult subtask is going to take all the time, basically. And the reason we are allowed to do this is because of the time sharing weight. So imagine that W and 1 and then 2 and 3 are 1/3. Then that's a factor of 3 to each time for each segment. So the factor of 3 already encompasses the number of subtasks. It says there are at least 3 subtasks. So 3 times the maximum is more than the sum. So this maximum makes it more efficient. We don't need to pay double for the decomposition. And what's cool is that we looked at one decomposition from N1, N2, N3, and star, but actually we can look at any decomposition, because this is what we're doing here is an analysis in hindsight of the behavior of the algorithm. The algorithm stops at some point. We know that, but there are several ways to look at what led to stopping at this point. And one way is to look at this N1, N2, N3, and star decomposition. Another one is let's skip N2 and just look at the search starting from N1 to N3. That doesn't reroute on N2. Maybe the root node at N2 has a weight that is very small. We gave it too little time, and that's not particularly efficient. So maybe N1, from N1, we're going to find N3 faster. So we can go from N1 to N3 to N star, or maybe directly from N1 to a star if there's no clue in the middle. There's no useful clue that gives us a good rerouting weight. And now we have a bound that is even stronger than what we had before, because we are allowed to look at every possible subtask decomposition, pick the best one in hindsight, and say that our bound is the maximum of the subtasks, the difficult subtasks on this decomposition. So if you look at the decomposition and the hardest subtask is too hard, then maybe you need to look at the different decomposition. All right, so this is the root LTS algorithm with just a few modifications. The first one is going to fold all the LTS instances into a single cost function for best first search. So now we don't have really this meta algorithm with different sub algorithms that we're starting. We just have one best first search with a cost function. So that's and that allows us to also make it more efficient. Like we don't need to calculate many things at the same time. There's even a faster algorithm that calculates basically almost only one instance per node. So order one calculation per node and not order number of instances. We are also going to allow the rerouting weights to be unnormalized because, well, sometimes it's quite useful. We can tighten the bounds that forcing the sum to be one a priori is a bit annoying. We're going to see an example of that later. And then we're going to also to allow the weights to depend on all the paths. So instead of assigning the weights at the very top root, we're going to assign the weights when we see them. So we see a new root node somewhere in the search tree, and we are going to start the search, but we can decide on the weight at that point based on all the paths. And we're going to replace TLTS with this D over pi thing ratio that we saw earlier. Okay, so just to give you the full theorem, we choose a subtask decomposition when we reach the node NT at step T, and T is bounded by the maximum of the subtask of the time it takes LTS to go from one root of the subtask to the next root, multiplied by the normalized time sharing weight, rerouting weight, where this is the normalizer. It's just the cumulative of all the weights up to the last step. And that's the maximum of the subtasks. Okay, so how does it work on the motivating example? Well, we say, well, the time sharing weight of the root, the rerouting weight is going to be 1. The rerouting weight at every clue is going to be 1 also, and 0 elsewhere. Fine. The probability is uniform, 1/2, 1/2. So the cumulative, the normalizer, is just going to be the sum of all the routing weights we see during the search. It's going to be at most 1001. Okay. Then we can look at the subtask decomposition. So maybe N1 directly to N star. That would be breadth first search, basically. But you can also split now at NC, the right clue. And we know that the time to reach N star is going to be bounded by the time sharing weight, which is the same for both cases, of the segment N1 to NC and the segment NC to N star. Both have a search time of 2 to the 50. The D over pi is actually going to be 50 times that. This is a little suboptimal. We pay a factor of 50, but it's you can actually remove it if you use something smarter. Right. So just by splitting the task into two subtasks right in the middle, we are square rooting the search time by just one little piece of information at the right place. So we don't need by contrast to the policy that needs to be really good almost everywhere, the rerouter needs to be good only once to really be helpful. And if it's good multiple times, it's going to be even more helpful. So if you can decompose into 3 segments, for example, this goes down exponentially as you have more segments. We also have a general lower bound for these types of clue environments where we can have clues everywhere and solutions everywhere. I'm not going to go into the details, but basically root LTS is optimum for that class of environments, whereas we can show that Levin tree search, as we said earlier, also struggles. But not only that, but even A star and weighted A star are going to struggle. They're going to take basically exponential time if you want to ensure that you're going to find the solution of 1 plus epsilon shortest solutions within a factor 1 plus epsilon. Right. So let's take a little example and let's instantiate the rerouter to explain a little how it works. Here's a level of Sokoban where we need to push all the 4 brown boxes on the blue spots. And we design a very simple policy, which is don't go into the walls. It doesn't work, it's not useful. And also don't undo what you just did. If you come from the left, there's no point going back left. But if you push a box, maybe that's needed. Okay, so with this very simple policy, LTS is going to take at most 200 million steps, which is a big number, but it's tractable. It's not great. And the question is, if we have this additional information in form of clues, can we go faster? How much faster can we go? And I said at the very beginning that we were using intermediate rewards for when we push boxes onto goal spots. Let's use that. And let's see how we can make it efficient and what the trade-offs are. So when we push the first box onto a goal spot, we're going to get a rerouting weight of 1. The second time we push a goal spot onto, a box onto a goal spot, but it's still the only box on the goal spot, you have a rerouting weight of 1/2. The third time, 1/3, 1/4, 1/5, and so on. Now, when you push 2 boxes onto 2 goal spots, or at the time you push the second box onto the second goal spot, you get a rerouting weight of 1, and the second time this happens during the search, you get a rerouting weight of 1/2, 1/3, and so on. When you push 3 boxes onto 3 goal spots, you get a rerouting weight for the first time of 1, then 1/2, 1/3, and so on. And when you get 4, well, you have solved the problem, so no need. Okay. If we design it this way, the cool thing is that we have a guarantee on the normalizer. We know it's going to be bounded by 3 times log t. So we pay a log factor, and a factor 3, compared to LTS without any clue. So now, if there's a clue that compensates for this factor, and also maybe a little more, we win. And the idea is that if there's a clue that's going to be on the solution path, and this is one of the first steps, first time in the search tree where it's going to happen, then that's going to help. If we need to search for many times 2 boxes and 2 goal spots until we find the right one, that's not going to help. But if it doesn't help, well, we pay a factor log t with the hope that maybe some other clue is going to help. And indeed, what happens is that the first box, pushing the first box, is not informative, or almost not informative. It's not worth it. So when we push 1 box onto one goal spot, in particular in this problem where the first box is misleading, because you shouldn't push it, otherwise you can't solve the problem. Let me show you why. You need to go around first, push the box from inside to the outside, then go push up, push from the outside to the inside, and then you can push this one last. But the thing is, because of this misleading box at the beginning, you're going to spend a lot of time thinking that's the right thing to do. So you have lots of clues that tell you, yeah, this is good, it's good. But the first time you see that you have a routing weight of 1, yeah, let's spend a lot of time here. And then 1/2, a little bit less, 1/3, 1/4, and so on. And the cumulative of this is going to be some log t thing. So it's not that much in total. And okay, at some point, you finally manage to push the second box onto a goal spot. And that's a lot rarer. And that's more likely to be on the solution path. Maybe it's not the right configuration, but maybe the second or third time you try, it's going to be the right configuration. So this number of times you have tried Q here is going to be small. And that's the factor you're going to pay. So 1/Q is your routing weight. And so as you pay as the time sharing weight, the inverse of the routing weight, then you're going to pay a factor Q. So if you have to try only a few times, you're going to pay a factor of the number of times you try. And it happens indeed that pushing the second box is going to be very informative. And then you find very quickly how to push the third box. And that also splits your search. And then you get to the fourth box. And indeed, if you look at the numbers in hindsight, it gives you that the time bound is going to be at most 3,000. So that's a really big reduction compared to the 200 million. It's basically taking the cubic root and multiplying by some factor that depends on the uncertainty of your rerouter. Okay? Yep. 5 minutes. Oh, 5 minutes. Okay, I'm almost done. All right, so next steps are we have some papers in the works. One is going to be published at ICML. And the idea is that there was a previous paper by the main author where they were using a VQ-VAE to define a sub-goal conditioned policy. So you generate explicit sub-goals, you condition your policy onto solving these sub-goals, and that allows you to learn something without even having solved problems. For this, you have a clustering algorithm that gives you the bottlenecks, and you try to get to the bottlenecks. So these are like interesting clues. So we figured this, and maybe it's a good idea to replace all this VQ-VAE with just clues for root LTS. And results are that works a lot better. It's much faster, easier to implement. You remove one neural network. And then we also figured, well, maybe we can use that with a heuristic distance, like the A-star kind of distance. What we're going to define is the routing way is going to be x of some alpha times the distance, or minus alpha if you have a negative value. So the further you are, the less you reroute. But if you're getting close, maybe that's a good place to start rerouting more. And so we have two rerouters, and these work pretty well on their own. But the even cooler thing is that you can combine them. So you just add the weights with some factor alpha here. You know that you're going to pay, in the worst case, for the cumulative factor of both of them together. So the cumulative of the first one plus the cumulative of the second one, so not a multiplicative of the two. So you're not paying too much compared to either. And you can even rebalance things. Actually, you should rebalance things so that you pay only a factor 2. And what happens is that then you can use the synergy of both rerouters. So if one router knows how to decompose in some situations and the other knows to decompose on other situations, then you can do both at the same time and split your sub into more subtasks, and so reduce the search time even more. And that works really well. It scales also much better than the previous algorithm when we increase the difficulty of the problems. We also have another problem, another paper in the works where we apply the same problems that we had before, plus more, but I'm not going to spoil all the fun. But some interesting results are initially for Rubik's Cube, we used like quite a few hours before we could get something that works well. And then 2 days before we get the policy that solves the all Rubik's Cube in 500 steps. Now it takes only 5 minutes of bootstrapping on the same kind of data set. So 5 minutes compared to just a couple of days. And not only that, but if you start with only Rubik's Cubes that are scrambled, not that much, not even difficult ones, like 10 steps at most, which is not completely random cubes, it still manages to generalize to solving all Rubik's Cubes. So here there's probably the decomposability of the context models that really helps, but the rerouter is able to take advantage of that really well, whereas LTS alone could not take advantage of that. So just the policy alone didn't help, but with the rerouter, we can generalize a lot better. And on Sokoban, so the same old set of problems, it just takes 1 minute of training to get to the same numbers. All right, so we have seen that time sharing is a very powerful and also very old idea that should be used in many other problems. There's one thing you should remember from this talk is time sharing. And we actually used it also for another problem where we solved another decade-old problems in heuristic search algorithms based on A-star something. I'm not going to go into the details now, but it really worked very well. And now, what's nice is that you have formal guarantees based on this simple time-sharing scheme. And also, context models are simple, effective, fast. So maybe neural networks are not always the solution. And maybe you need to think about other things that might work well. And next steps are, well, I think there are lots we can do with root LTS. We can instantiate the routers in many different ways to generate specific algorithms with formal guarantees. And then, of course, apply it to actual real-world application, not just puzzles. That's that's in the works. We'll see how it goes. Wish me luck. We'll see. Right. I think I'm done, and that's for later if you want to talk about it. Thank you.